Okay, what I was writing down when I was cut off is that we see that when we have A plus times h bar omega plus h of psi, and this comes from the fact that h bar omega times a plus a minus plus 1/2 is equal to the one way of writing the Hamiltonian operator. Okay, and but we know that the Hamiltonian operator acting on psi just gives us the energy, a number, times psi, and we rearrange this. Okay, so we have a plus times the energy plus h bar omega times psi, and then we realize that this is just a number. E plus h bar omega is just a number. We know the energy. We stipulated that we know the energy. H bar omega is just a number, and so we have a number always commutes with an operator. So some number times a function always is equal to that same function times the number, and so we can rearrange this and recover our a plus psi. And remember, what we were doing is we applied the Hamiltonian operator onto a plus the operator, the new function a plus psi, and what we get back is a number e plus h bar omega times that same function back. And so this is another eigenvalue problem, but now what we find is that we have a new energy which has been raised by the quantity h bar omega. Okay, and so what we find is that a plus psi is actually also a solution to the Schrodinger equation in addition to psi, but now the energy of that solution, the energy of that function a plus psi, is equal to the original energy plus the quantity h bar omega. Okay, and that, if we did the same kind of procedure, but now we used the other way of writing the Hamiltonian operator, h bar omega times a minus a plus minus 1/2, and we basically applied that to a minus psi. Okay, so instead of a plus psi, we applied to a minus psi this other form of the Hamiltonian operator. What we'd find is that a minus psi is again a solution of the Schrodinger equation, but now with energy e minus h bar omega. So that the energy that we started with minus the quantity h bar omega. And so now we see maybe why we call these the raising and lowering operators. Okay, a plus acting on a wave function gives us a new wave function, which is a solution, a new eigenfunction, which is a solution to the Schrodinger equation, but with the energy raised by a discrete amount h bar omega, and a minus lowers the energy by h bar omega. Okay, and so these operators, the raising and lowering operators, allow us to go up, to go from one solution of the Schrodinger equation to the next, up or down, in energy. A plus to go up in energy, a minus to go down in energy. And so if we can find one standing wave solution, one stationary solution to the Schrodinger equation, then we can find all the others by successive application of either a plus or a minus. Okay, and so that's why we did this solution, because it's very elegant. You just need to find one solution, and then you can find all the rest using these raising and lowering operators, all with relatively simple math and the concept of operators. Okay, so I've written what I just said. The raising and lowering operators allow us to go from one solution of the Schrodinger equation up or down in energy to the next. So that implies that we just need to find one stationary solution to find all the others. Okay, I should also point out that what we've just discovered is that because we basically assumed an arbitrary function psi, if that psi in this analysis, if that psi happened to be an eigenfunction, psi sub n, we know that they're going to be discrete states, quantized states, and if psi happened to be one of those eigenstates, then what we've just found is that the eigenstates are all separated by equal amounts in energy equal to h bar omega.